Designing electrical projects at 277/480 volts requires a strong foundation in electrical principles and adherence to safety standards. It is crucial to understand Ohm's law, voltage drop calculations, and power calculations. Experience in designing and implementing electrical systems up to 208 volts is helpful, but specific knowledge of the National Electrical Code, or NEC, requirements for higher voltage systems is essential. To step up the voltage, a transformer designed to increase the voltage from 120/208 volts to 277/480 volts is necessary. Ensure the use of insulated conductors rated for 277/480 volts. All electrical components, including switches, receptacles, lighting fixtures, and any other components, must be rated for 277/480 volts. A suitable electrical enclosure is needed to house the transformer and other electrical components, protecting them from environmental factors and accidental contact. Design considerations are paramount. Voltage drop calculations are critical to determine the voltage drop in the conductors and components, ensuring proper voltage levels at the end of the circuit. Specify appropriate breakers or fuses to protect the circuit from overcurrents and short circuits. Proper grounding must be implemented to protect against electrical hazards and ensure personnel safety. Verify that all components used are rated for the higher voltage to prevent failures and hazards. Conduits or raceways that meet the NEC requirements for 277/480 volt installations are mandatory for protecting conductors and providing a safe wiring system. It is highly advisable to consult with an experienced electrical engineer or electrician for guidance and safety precautions, especially when working with higher voltages. Obtain all necessary permits and inspections to ensure compliance with local regulations and codes. Thoroughly test the system before energizing it to identify and correct any potential issues. Always use appropriate personal protective equipment, or PPE, and follow established electrical safety practices to minimize the risk of electrical shock and other hazards. In more detail, let's explore these minimum requirements. Firstly, a strong understanding of electrical principles is the cornerstone of any successful high-voltage project. This includes a firm grasp of Ohm's law, which defines the relationship between voltage, current, and resistance. Understanding how voltage drops occur along conductors and through components is crucial for ensuring adequate voltage at the load. Power calculations are essential for determining the appropriate size of conductors, transformers, and protective devices. Secondly, while experience with 120/208 volt systems is valuable, it is not a direct substitute for knowledge of high voltage specific requirements. The NEC provides detailed guidelines for the installation and operation of electrical systems at all voltage levels. Familiarity with the relevant articles and sections of the NEC is mandatory for ensuring compliance and safety. A voltage step-up transformer is a critical component for converting lower voltage power to 277/480 volts. The transformer must be appropriately sized for the load and must meet relevant safety standards. The transformer should be installed in a suitable enclosure to protect it from damage and to prevent unauthorized access. Electrical wiring must be selected and installed according to NEC requirements for the specific voltage and current. Conductors must be insulated with materials rated for the applied voltage. The size of the conductors must be adequate to carry the load current without excessive voltage drop. Electrical components such as switches, receptacles, and lighting fixtures must be specifically rated for use at 277/480 volts. Using components not rated for the appropriate voltage can result in equipment failure, fire hazards, and electrical shock. An electrical enclosure serves to protect electrical components from environmental factors, physical damage, and unauthorized access. The enclosure must be appropriately sized to accommodate the components and must be rated for the environment in which it is installed. One design consideration is voltage drop. Voltage drop occurs when electrical current flows through a conductor, resulting in a decrease in voltage at the load. Excessive voltage drop can cause equipment malfunction, overheating, and reduced efficiency. Voltage drop calculations should be performed to ensure that the voltage at the load remains within acceptable limits. Circuit protection is essential for preventing damage to equipment and for protecting personnel from electrical hazards. Circuit breakers and fuses are designed to interrupt the flow of current in the event of an overcurrent or short circuit. The size and type of circuit protection devices must be carefully selected to match the characteristics of the circuit. Grounding provides a lower impedance path for fault currents to return to the source, minimizing the risk of electrical shock. The grounding system must be properly installed and maintained to ensure its effectiveness. Component ratings must be verified to ensure that all components are rated for the applied voltage and current. Using components with inadequate ratings can result in equipment failure, fire hazards, and electrical shock. Conduits and raceways are used to protect conductors from physical damage and environmental factors. The type of conduit or raceway must be selected according to NEC requirements for the specific application. In addition, consulting with an experienced electrical engineer or electrician is crucial for ensuring the safety and compliance of the electrical system. They can provide valuable insights and guidance on the design, installation, and testing of the system. Obtaining the necessary permits and inspections is essential for ensuring that the electrical system meets all applicable codes and regulations. Permits and inspections help to ensure that the system is installed safely and correctly. Testing the system thoroughly before energizing it is important for identifying and correcting any potential problems. Testing can include insulation resistance testing, continuity testing, and voltage testing. Using appropriate PPE such as gloves, eye protection, and arc-rated clothing is essential for protecting personnel from electrical hazards. Following established electrical safety practices such as lockout/tag-up procedures is also crucial for preventing accidents. When working with 277/480 volt systems, additional safety considerations are required. Firstly, increased insulation requirements. Higher voltages require greater insulation thickness and quality to prevent arcing and insulation breakdown. Secondly, arc flash hazards. The potential for arc flash is greater at higher voltages, requiring appropriate arc flash protection measures such as arc-rated clothing and barriers. Thirdly, clearance distances. Increased clearance distances are required around energized equipment to prevent accidental contact. Fourthly, equipment maintenance. Regular maintenance is essential to ensure the continued safe operation of high-voltage equipment. For example, consider a scenario involving the design of a new lighting system for a large warehouse. The warehouse owner wants to use energy-efficient LED fixtures that operate at 277 volts to reduce energy consumption. To design this system safely and effectively, firstly, you must have a strong understanding of electrical principles, including Ohm's law, voltage drop, and power calculations. Secondly, you must be familiar with the NEC requirements for 277-volt systems, including conductor sizing, overcurrent protection, and grounding. Thirdly, a step-down transformer will not be required as you are stepping from 480 to 277 volts. Fourthly, wiring must be installed in conduit to protect it from physical damage. Fifthly, you must select LED fixtures that are specifically rated for 277 volts. Sixthly, you must calculate the voltage drop in the circuit to ensure that the fixtures receive adequate voltage. Seventhly, you must install appropriate overcurrent protection to protect the circuit from overloads and short circuits. Eighthly, you must properly ground the system to protect against electrical shock. Ninthly, you should consult with an experienced electrical engineer or electrician to review your design and ensure that it meets all applicable codes and regulations. Tenthly, you must obtain the necessary permits and inspections before energizing the system. 11thly, you must test the system thoroughly to ensure that it is working properly. By following these steps, you can design a safe and effective 277-volt lighting system for the warehouse. Let's consider another example, this time for a manufacturing facility. the facility needs to install new machinery that operates at 480 volts. Firstly, you must possess the required electrical knowledge, including a deep understanding of three-phase power systems, motor control circuits, and safety interlocks. Secondly, familiarity with NEC articles pertaining to motors, machinery, and industrial installations is crucial. Thirdly, a step-up transformer might be necessary if the facility's incoming voltage is lower than 480 volts. The transformer's capacity must be sufficient to handle the machinery's load. Fourthly, wiring must be sized appropriately for the machinery's current draw, considering directing factors for ambient temperature and conduit fill. Fifthly, a motor starter with overload protection is essential to control the machinery's motor and protect it from overheating. Sixthly, grounding of the machinery frame and associated equipment is vital to prevent electrical shock hazards. Seventhly, safety interlocks, such as emergency stop buttons and safety guards, must be integrated to protect personnel. Eighthly, a qualified electrical engineer should review the design and ensure compliance with all applicable codes and standards. Ninthly, thorough testing and commissioning of the machinery and its electrical connections are necessary before putting it into operation. Additionally, arc flash studies may be required to determine the appropriate personal protective equipment, or PPE, for personnel working on or near the 480-volt equipment. Proper training for operators and maintenance staff is essential to ensure safe operation and maintenance practices. High-voltage systems, such as 277/480-volt installations, pose significant risks if not handled correctly. Failure to adhere to safety guidelines and regulations can lead to serious injury, property damage, and even fatalities. Always prioritize safety and consult with qualified professionals when working with high-voltage electrical systems. Continuous learning and staying updated with the latest codes and standards are crucial for maintaining competence and ensuring safety in electrical work. When designing a project for 277/480 volts, a comprehensive understanding of electrical principles, code compliance, and safety practices is absolutely necessary. Neglecting any of these aspects can lead to hazardous situations and costly mistakes. Before commencing any work, it's highly recommended to seek guidance from experienced electrical engineers or certified electricians who can provide valuable insights and expertise. They can help ensure that the project meets all requirements and is executed safely and efficiently. Furthermore, obtaining the necessary permits and approvals from local authorities is essential to comply with regulations and avoid potential legal issues. These permits ensure that the project undergoes proper inspection and meets the required safety standards. Thorough testing and commissioning of the electrical system after installation are crucial to verify its proper functioning and identify any potential problems. This includes testing installation resistance, continuity, and voltage levels to ensure that all components are operating within their specified limits. Investing in appropriate personal protective equipment, or PPE, such as insulated gloves, safety glasses, and arc flash suits, is a must to protect oneself from electrical hazards. It's also important to follow established safety procedures such as lockout/tagout to prevent accidental energization of equipment during maintenance or repairs. Regular inspections and maintenance of the electrical system are necessary to identify and address any potential issues before they escalate into serious problems. This includes checking for loose connections, damaged wiring, and corroded components, as well as ensuring that all safety devices are functioning correctly. In addition to technical aspects, effective communication and collaboration among all stakeholders, including engineers, electricians, contractors, and building owners, are essential for successful project completion. Clear communication helps to ensure that everyone is on the same page and that all requirements are met. By following these guidelines and prioritizing safety, one can minimize the risks associated with working with 277/480 volt systems and ensure a safe and reliable electrical installation. In summary, designing for 277/480 volts demands a holistic approach encompassing theoretical knowledge, practical skills, code compliance, safety awareness, and effective communication. Continuous learning and adherence to industry best practices are vital for staying competent and ensuring the safety of oneself and others. Furthermore, documentation is a critical aspect of any electrical project, particularly those involving higher voltages like 277/480 volts. Accurate and detailed documentation serves several purposes. Firstly, it provides a record of the design, installation, and testing processes, which can be invaluable for future reference, troubleshooting, and maintenance. Secondly, it ensures compliance with regulatory requirements and facilitates inspections by local authorities. Thirdly, it helps to communicate essential information to stakeholders, including building owners, facility managers, and maintenance personnel. The documentation package should include several key components. Firstly, detailed electrical schematics showing the layout of circuits, components, and wiring connections. Secondly, a bill of materials listing all components used in the project, including their specifications and ratings. Thirdly, calculations for voltage drop, conductor sizing, overcurrent protection, and grounding. Fourthly, test reports documenting the results of insulation resistance tests, continuity tests, and voltage tests. Fifthly, operation and maintenance manuals providing instructions for the safe and efficient operation and maintenance of the electrical system. Sixthly, as-built drawings reflecting any changes made during the installation process. In addition to these documents, it's also important to maintain records of all inspections, permits, and approvals obtained for the project. These records demonstrate compliance with regulatory requirements and provide evidence of due diligence in ensuring safety. The documentation should be organized in a clear and logical manner, making it easy to access and understand. Electronic copies should be stored securely, with backups in place to prevent data loss. Hard copies should also be retained in a safe location. Regular updates to the documentation should be made as needed to reflect any changes or modifications to the electrical system. This ensures that the documentation remains accurate and up to date. By maintaining comprehensive and accurate documentation, one can facilitate the safe and efficient operation and maintenance of the electrical system, ensure compliance with regulatory requirements, and minimize the risk of electrical hazards. Finally, the ability to troubleshoot electrical issues is a crucial skill for anyone working with 277/480 volt systems. When problems arise, a systematic and methodical approach is essential to identify the root cause and implement effective solutions. Before commencing any troubleshooting activities, it's crucial to ensure safety by de-energizing the affected circuit or equipment and following appropriate lockout/tagout procedures. Using personal protective equipment, or PPE, such as insulated gloves and safety glasses, is also essential to protect oneself from electrical hazards. The first step in troubleshooting is to gather information about the problem, including when it started, what symptoms are present, and any recent changes or modifications to the electrical system. This information can help to narrow down the possible causes of the problem. Next, visually inspect the circuit or equipment for any obvious signs of damage, such as burnt wires, loose connections, or broken components. Use a multimeter to test for voltage, current, and resistance at various points in the circuit to identify any anomalies or discrepancies. Consult the electrical schematics and documentation to understand the normal operation of the circuit and identify any deviations from the expected behavior. If the problem is not immediately apparent, use a process of elimination to systematically test different components and sections of the circuit until the fault is located. Once the fault has been identified, implement the necessary repairs or replacements to restore the circuit to its normal operating condition. After completing the repairs, thoroughly test the circuit to ensure that the problem has been resolved and that all components are functioning correctly. Document all troubleshooting activities, including the symptoms tests performed, findings, and repairs made. This documentation can be valuable for future reference and for identifying any recurring problems. If the troubleshooting process requires specialized knowledge or equipment, don't hesitate to seek assistance from experienced electrical engineers or certified electricians. They can provide valuable expertise and guidance to help resolve complex electrical issues.